Okay, so let us continue with the discussion we had started last time on the practical aspects of NMR. We have gone through certain discussion already, so we will continue from where we left. We discussed about the various components of the FT-NMR spectrometer, the important things about the magnet, the console, and then of course on the desktop what all you can, and then we talked about the frequency log, the shim system, transmitter controller, RF transmitter, pulse programmer, receiver. We talked about these ones. So this is the general view of the modern NMR spectrometer. This is the magnet here, and then you have the console, then you have the desk, the computer for monitoring the whole thing. This we discussed already. We discussed about the magnet, superconducting magnet. Special property of superconductivity is exploited here. Superconductivity means the resistance is zero. Therefore, once the current is going inside a coil, it will persist. It's a persistent current. It continues to go. Therefore, the magnetic field generated is absolutely stable. And you can generate very high currents in the coils because you get a large number of turns. So in order to increase the number of turns, the field generated overall depends on the total number of turns in the coil. And this is enhanced by a special design of the magnetic, these coils, superconducting coils. And that also we showed here that how the highly technologically very precise system of making the superconducting wire. So so many superconducting wires are drilled into one particular copper wire, and the current essentially flows through the superconducting wires only. It doesn't go through the copper because the copper has the resistance and superconducting wire don't have resistance, and therefore the current will flow naturally through the superconducting wires. So whenever there is a quench or anything like that, then of course the energy has to be dissipated immediately, and there the copper becomes very helpful. And that is why it is designed in this manner. And there are where it is kept, and the design of that is shown here, indicated that. So the new elements in the FT-NMR spectrometer compared to the standard spectrometers which were used earlier, which had electromagnets, they had serious limitations with respect to the strength of the magnetic field, the stability of the magnetic field, the temperature of the magnets, and so on and so forth. Because when the current is passed, the heat is dissipated, and then of course that causes heating of the magnet, and that decreases the stability of the magnet. And all those problems are gotten over when you have a superconducting magnet. We can reach very high magnetic field, and in a very small area, the whole magnet can be contained. So that was the main significant advantage of superconducting magnets. Then you have these things like high power transmitters. You need to have very high power transmitters to do a pulse generator, the pulse programs. So you need a high power transmitter. In the earlier cases, there used to be very, very low power transmitters. In the CW magnets, CW spectrometers, the power was very, very low. Here you need very high power transmitters because you apply a pulse. The pulse requires very high power. And that is why you need to have high power transmitter and the pulse generator. Then the data is collected in the form of digitized points. So therefore, there is a digitizer which actually collect the data in the form of points. Okay, so there is a digitizer. Then your filters, the filters will actually take care of the removing the unwanted part of the spectrum, unwanted part of the excitation. All that is done by the filter. Various kinds of filters, low pass filters, high pass filters, band pass filters, various kinds of filters are there, and these are employed in the console to select out whatever is required, select out whatever is not required, keep and whatever is required. Then the receiver is the crucial part of the system, is the detector. So the signal that is coming, it is collected in the receiver, and now here is a digitized signal. Okay, so this is an induced signal, and this compared to what it was in the CW system, here it is the digitized signal which comes from the digitizers. Okay, and then we also gave here some general theorems of Fourier transforms, which you already defined this earlier. We don't want to go into these details once more. And some important theorems are listed here because we are going to use them, especially this one. Delayed acquisition, the data acquisition, what happens when you have delayed acquisition? We will see the consequences of this as we go. And then, of course, we also talked about, notice, let me mention this once more. that if we have a delayed acquisition, that is, if the data acquisition delayed by time t, then when you do Fourier transformation, the spectrum acquires an additional phase, which is e to the I omega delta t, and it is frequency dependent. So this is an additional phase which will come on the spectrum. So delta t represents the delay in the start of data acquisition. The frequency domain spectrum is phase modulated by delayed acquisition. And you will see that this is actually very special to Fourier transform NMR. It is not there for CW NMR spectrometers. This is there for Fourier transform NMR spectrometers only because of digitized acquisition of the data. And then the area under the curve, area under this frequency spectrum is equal to the time point 0, in amplitude of the time point 0 at t is equal to 0. So f of 0 is equal to the integral of the all the spectrum, FW dW, integral FW dW. Therefore, the first point is very crucial and it will tell you a lot of things about the spectrum. The integral of the spectrum is equal to the value of the first point in the FID. Okay, now there's another important theorem was the convolution theorem. That is, you can multiply two time domain functions. This results in the frequency domain a convolution of the two Fourier transforms, individual Fourier transforms. F of t gives individually Fourier transform gives the spectrum f of w. G of t individually Fourier transform gives the GW. But if you take the product here, f of t into g of t, then you have this convolution of the two functions f omega and into g omega. And this convolution is defined in this manner. See, the calculation of this convolution is used to simplify the spectrum. Look at the appearance of the spectrum, and you will see that as we progress, we will see how this is important. And it's convenient to perform this convolution in the time domain rather than in the frequency domain. In the frequency domain, it is an integral. This process is an integral, whereas in the time domain, it is a simple multiplication of the two functions. Therefore, it is easier to do this operation in the time domain rather than in the frequency domain. You need to do this to smoothen your data. And the convolution essentially helps you to smoothen the data and make a better looking spectrum. And that is easily done in the time domain because the convolution in the reverse Fourier transform, it is like the multiplication of the two time domain functions. Okay, digitization. Digitization is another very crucial thing. And the time domain data here is basically analog signal is f of t. And how do you digitize it? You multiply by this kind of a function, delta function. This is the series of delta functions. N goes from minus infinity to infinity. See, for example, if n is equal to 0, then delta t, what is delta t? The function delta, the delta function, for those of you who are not familiar with the delta function, it has a value when it is equal to 0. The variable is 0, it has infinite value. But when it is anywhere away from that, it is 0. So therefore, you can individual points you can represent as multiplication of f of t with the delta function. So when the t is not equal to any of these numbers, its value is 0. And therefore, you can digitize the data in that way. When it is equal to any of these points, then it has an infinite, very large value. And that, of course, its amplitude is given by this f of t. So therefore, you can divide this entire signal, which is analog signal, into individual points like this. When t is equal to nt, any of these, n is equal to 1, 2, 3, 4, 5, and the tau is the time between these points here. When it is equal to any one of those, you have a value. Otherwise, it is 0. Because the delta function is the Dirac delta function has that property. So it will give you 0 when it is not equal to n tau. Otherwise, it is equal to a large value, and that is multiplied by the f of t. Whatever is the value of that, it gives you that one. Integral of the delta function is equal to 1. So therefore, this is how the digitization is done. And when you do the Fourier transform of such a digitized FID, then you get a frequency domain spectrum, which is also digitized. The digitized spectrum, here again, it is a multiplication of the f of w into the series of delta functions in the frequency domain. Here the delta functions were in the time domain. Now here the delta functions are in the frequency domain. And these points are separated 1 by tau. See, the whole thing is when you do this operation, you get a function which is like this, 1 by tau f omega minus n by tau. So you see this, what it means is that you get a series of spectra. N is equal to 0 gives you f of w, which is entire spectrum. Okay, full f of w. Okay, and then if n is equal to 1, this is another spectrum, but it is displaced from f of w by 1 by tau. 1 by tau. 1 by tau is how much? Tau is your dwell point. So therefore, it is one entire spectral width is gone there. So therefore, you get a series of spectra. If you combine this here, when you look at this, n is equal to 0, n is equal to -1, n is equal to +1, -2, +2. So whole range of spectral features you get spectra you will get. Of course, the filters are used to eliminate those. Filters are used to pick up only the one which is n is equal to 0. However, certain components of n is equal to 1 and -1 do show up in your spectrum, and that we will discuss in the C as we see when we talk about the folding of the spectrum. So therefore, the digitization has this consequence. So we get a large number of spectra which are separated by 1 by tau, and tau is your dwell time. Okay, so therefore all your data are separated by that much amount. And this is the FID. The FID now is in digitized points as indicated there. So all of these points, when you Fourier transform it, you get the frequency domain spectrum, which is again like this. Now, if there are n points here, so there in the total frequency domain spectrum also there will be n points. Okay, but in the frequency domain spectrum has real and imaginary components, and each one of them spreads the entire frequency range. Therefore, there will be n by 2 points in the frequency in the real points, this n by 2 real points and n by 2 imaginary points. And each of all of these points, n by 2 points, represent the entire spectrum. So therefore, that is the kind of a digital resolution you will have in an NMR spectrum. Depending on the number of points you have in the FID, you will have half the number of points of those to represent in your NMR spectrum. So and accordingly, you can choose how much data points you should have, how to increase the number of data points. All of this is cosmetics, and which we will see how one can improve this. Okay, so I think we probably stopped here last time, and then we will continue from here. Now, some other practical aspects of the excitation, which, okay. So you see, this is a little bit of a repetition in the sense that when you apply a pulse here like this for a time tau, let's say this is the period TP. Let me call it, okay, tau is called here tau. So this length here is tau. If you apply an RF for a period tau, remember, this tau is different from the previous tau which I mentioned. There, the tau was the dwell time. Here it is not. Here it is the time for which you apply the pulse. This is also called as the pulse width. So for how long you apply this RF, and that is the tau. And its Fourier transform of this time domain function is a frequency domain spectrum which is looking like this. The central frequency is omega naught, because that is the same frequency which you are applying here, omega naught, and that is applied for a period tau. The central frequency has the maximum amplitude, but it also generates a larger number of other frequencies which are different amplitudes. So you see that the amplitude falls off like this, and it comes to 0. This is the kind of a sinc function, sin x by x function. Okay, sinc function is sin x by x type of function. So this is, it comes to 0 at 1 by tau. So the 1 by tau is a 0, and all along from here to this peak, various kinds of frequencies are generated with the different amplitudes. Notice this, how much should be the tau? So if you have tau is equal to, let us say, 1 second, if what happens then it is 1 hertz, 1 by tau is 1. So therefore, you will have a very narrow excitation. Very narrow excitation. If tau is equal to 1 second, you will only have 1 hertz on either side. So therefore, when you apply soft pulses, you will have to apply long pulses. It has to be, there's an inverse relationship between the hardness of the pulse and the length of the pulse. So if you apply for a short period tau, then of course the bandwidth you cover in this is going to be larger, and the amplitudes also are going to be very. So therefore, when you apply onto a selective pulses, your pulse has to be long. So typically, when we say we apply selective pulse over a range of 20 hertz or 30 hertz and 40 hertz like that, then you will have to have a very long pulse. If you want to excite a range of about 1000 hertz, then of course your tau has to be much shorter to cover that area. So suppose I have tau is equal to 10 microseconds. Then how much is this? This is 10 to the power 5. 10 to the power 5 is 100 kilohertz. So 100 kilohertz here and 100 kilohertz here. So the total of 200 kilohertz will be covered. So in order to apply, of course, the power required will be high. When you want to apply it for a short period tau for 10 microseconds, you can afford to have a high power. because then it will not cause any burning of the probe and things like that. If you apply a high power for 1 second, then you will burn the probe. So this is the one has to be extremely careful with regard to this, because it generates a lot of heat. So if you apply high power pulse for a very long time, then the system will burn itself. So, but we apply for a short period, like 2 microseconds, 10 microseconds, then there is no danger. So you can apply for a short period and you can excite your whole range of frequencies, 200 kilohertz. However, all these 200 kilohertz are not useful because they have different amplitudes. So if you want to have uniform excitation of your frequency range, so let us say you have a frequency range of about 10 kilohertz. So then you have 5 kilohertz on this side and 5 kilohertz on this side you can excite. Then it is certainly you can choose a small area here which is about 5 kilohertz. Compared to the 100 kilohertz, choose the 5 kilohertz on this side. So that is not a problem. You do have a uniform excitation over there. The amplitude is similar. So the power is proportional to the square of the amplitude. So if H1 is the amplitude of your RF, then the power is proportional to H1 square. Okay, so therefore you generate a very high power with the short pulse. And when you do this, what is the consequence? You, as I said, we can select here. Now we can select a small portion here, which is about 10 kilohertz. You can cover this, and it will cover the entire spectral region of your interest. So that is what you need to do when you are doing pulse excitation, and you do Fourier transformation to detect those. Okay, detect your signals. Okay, now the consequence of what we said earlier shows up here. Now, where should I put the carrier frequency? Carrier means whatever is the spectrometer frequency which is going to be used for exciting your magnetization, exciting all your spins. Now, let us say you have a 600 megahertz spectrometer. Now, your molecules may have resonances which are not exactly at 600 megahertz, but slightly away from there. 600 megahertz plus about some 10,000 hertz away, or 20,000 hertz away, or even 30,000 hertz away. Then if you put the carrier there, your spectrometer frequency at that point, then you will not be able to excite all your frequency region properly, because this will be far away from that omega naught frequency. The amplitude of the RF is going to be small in that place. Therefore, excitation efficiency will be small. You need to have highest excitation efficiency. Therefore, your spectral region must come in this region. The spectral region must come in this region, which means your carrier frequency has to be at omega naught. But a priori, you do not know omega naught, right? So you have generated a certain magnetic field with a certain current. So it has generated a certain with 600.1 to 600.13 carrier with the spectrometer frequency. Now you will have to shift this frequency. You'll have to shift this frequency to the region of your interest where your resonances are going to come. Therefore, this frequency is shifted to a particular point, and then therefore it is called as the carrier frequency. You can move this around. You can use 10,000 hertz or 20,000 hertz, things like that. You can move this. Uniform excitation of all resonances, it is necessary to move the carrier frequency to the region of interest. Okay. Now, how do we generate this? Now, here, this is the electronics comes into the picture. You have the main spectrometer, which is generating the frequency of, let us say, 600.1 megahertz. Okay. Now, your region of interest is only 10 kilohertz, about 30 kilohertz away from that 600.1 megahertz. Therefore, what you do is you add this frequency externally to this 600.14. You have omega naught is your spectrometer main frequency, plus minus you add a delta omega naught, which is your offset. This is your offset. You shift this from the other side, and this frequency is generated by your electronics in the console. Okay, and that is added here to get the main frequency. Then your offset, the spectrometer frequency will now be at this point. It will produce the same power. So it's basically shifting the frequency, not changing the power. The power will remain the same. It is only shifting the frequency. So that is why you call it as the offset of the carrier frequency. And you need to optimize this. It can be different for different systems. For different nuclei, it can be different. Therefore, you will have to shift it differently for different carbons or protons or nitrogen. This can be different for different ones. Therefore, you need to optimize that. And this often is done by trial and error. This is you put a large frequency initially so that you have approximately where the thing is, and and you keep shifting this until you get the maximum intensity of your signals. When you get maximum intensity of the signal, that means, okay, you are at the right place, you get good, the carrier offset. Okay, the phase of the RF pulse, of course, this we discussed already, that phase is, we can apply the pulse along the x-axis or the y or the minus x or the minus y-axis, and accordingly your signal will also appear in that manner. Your detector, the receiver phase has to match this receiver, the pulse phase, signal phase, and that is how you get the different signals. This we have talked about it earlier. So you had the phase of the FID, your 90-degree X pulse takes the magnetization to the Y minus Y, and then your detector is put down here. So if you are collecting after the magnetization is rotated onto the minus Y axis, and if you detect the Y component of this, if the detector is placed on the Y axis, then you get a signal which is going like this, which is M minus Y. And if you put the detector along the X axis, then you start from 0 because the magnetization is here, your detector is here, therefore it starts from 0. Initial intensity is 0, it goes as a sine wave, but then it decays. It decays, both cases, the signal decays. This decay happens because of the transverse relaxation. So all the frequencies, the FID contains the summation of all the frequencies present, same here and same here, and this will be all sine components, and here it will be all cosine components. The consequence of this will be in the form, in the phase of the NMR spectrum. What magnetization you collect and what you, our Fourier transform it will show up in the phase of the spectrum. That is what is indicated here. If we have a FID which is looking like this, it will give a signal phase which is absorptive signal like this, because the f of naught is greater than 0. Remember, f of naught is the sum integral of the entire spectrum. Integral of the entire spectrum has to be positive, has to be greater than 0, and therefore it is absorptive signal like this. If you have a FID which is like this, then you have the signal which is dispersive in nature, which has 0 intensity at the resonance position, and it goes up and down on either side. So there is a dispersive nature. If your signal is like this, FID is like this, this happens according to the pulses which you applied on the top there, where the initial magnetization is with respect to the detector. The detector is kept at the same place, but you are changing the phase of the RF, so you are producing magnetizations along different axes, and you start collecting as they rotate in the transverse plane. Therefore, you have different forms of the FIDs. This will result in different phases of the NMR signals. Okay, now single channel and quadrature detection. Now, FID, as we said, this is like this. Let us say it is a cosine function. A cosine function, this is a cosine function, right? We wrote there earlier as a cosine function. This is cosine omega it. The cosine omega it consists of two frequencies. Okay, cosine omega it, let me write that here. Cosine omega it is equal to half e to the I omega it plus e to the minus I omega it. Okay, notice this I is different from this I. This I is the root minus 1, under root minus 1. This I is the index for the frequency. Okay, when you do Fourier, therefore there are two frequencies here, one omega I and minus omega I. And assume that we have got the pure phase, absorptive phase. So you get two frequencies here, omega I minus omega I. Two frequencies we get. This is artifact actually. Your frequency is only one, but it is a detection process. You are collecting only the cosine signal, the Y component of that. Therefore, the Fourier transformation of that is giving you only as two frequencies. Now, if I do collect the X component of that, now this will be a sine function here. The sine function which is decaying. Now, sine function, however is the sine function? Sine omega it is equal to 1 by 2i e to the I omega it minus e to the minus I omega it. Okay. Now, so therefore, this will again produce two frequencies, but they have opposite signs, plus and minus. And of course, it will produce a dispersive nature because of this I. This is 90 degrees out of phase with respect to the x-axis. This take it as the imaginary component. This means is along the y-axis. But you can do a phase correction on that one after that. So let us say we get, after that one, you get two absorptive lines, but they will have two opposite signs. Now, if you add these two, which means you collect both of the X and the Y components of your signal, then you will see that you get only one frequency, and that is your actual frequency. So this is called as a quadrature detection. So in single channel detection, you collect only two, they will get both the frequencies. Therefore, that will determine where you want to put your carrier frequency, because you don't want artifacts in your middle of the spectrum. So you want only the real frequencies present in your spectrum. In the single channel detection, if you have a certain spectral weight, okay, we'll come to that. We'll come to that later. Okay, so this allows discrimination of positive and negative frequencies. Okay, so with the quadrature detection, you collect both X and the Y components. In the case of single channel, you collect only the X component or only the Y component. If that will generate after Fourier transformation two frequencies. Okay. All right. So before we go here, let me also show here that this, with regard to the offset, where we should keep the offset when you do single channel detection or quadrature detection. If you are doing single channel detection, where you should keep your offset. Suppose your spectral width is from here to here. All your lines are here in this. Okay. You have to keep your offset at this point. This is the place where the offset. You cannot keep it in the middle here. Because when you keep it in the middle, it will Fourier transformation will produce you two frequencies, plus omega and minus omega n, and they will overlap in your spectral region. So therefore, the offset has to be kept at one end, either at this end or at this end, doesn't matter. When you keep it at this end, it will produce your real frequencies here, but the artifactual frequencies will be present on this side. We don't care about it. That can be filtered out. That can be filtered out. However, so when you put the carrier here, your maximum spectral region is this. The largest spectral frequency, omega max is going to be this. Okay, from here to here. So that will determine your digitization interval. And in the case of quadrature detection, where you put your carrier, now since I'm able to distinguish between the positive and negative frequencies, if my spectral region is here, I can put the carrier here. I can put the offset here, because it is able to distinguish positive and negative frequencies. With respect to this, what I mean positive and negative, I call this as positive and this as negative. Frequencies which are on one side of the carrier are positive, which are on the other side of the carrier are negative. So therefore, this is called as discrimination of positive and negative frequencies. Okay, and that is achievable by detecting both the X and the Y components of your spectrum. Okay, signal digitization and sampling. So as you said, the signal has to be digitized to collect the data at this point. Now, how much should be the interval between the 2 points? That is the important question. The time interval between two consecutive points is a constant for the whole length of the FID and is called the dwell time. And I call this as, let us say, tau here. This is determined by the next theorem, which states that to represent a sine or a cosine wave precisely by digital points, there must be at least 2 points per cycle of the wave. Okay. Therefore, dwell time is selected to suit the largest frequency in the spectrum. So 2 times omega max is called the next frequency. Now, omega max will vary from quadrature detection to single channel detection. Okay. So typical, but this law is the same. Tau is equal to 1 by 2 times omega max. That should be the time interval between two consecutive data points. Okay, this is called the next frequency, and this is the rule which is there. This is standard rule. You need to represent a complete cycle, a sine wave. You need to at least 2 points per. So once you choose it for the largest frequency, what happens for the smaller frequencies? There will be obviously more points in the cycle. So if I have for a largest frequency is, let us say, one large frequency and a small frequency, corresponding to this large frequency, I have data points at least 2 points, then automatically the FID is the summation of all the frequencies at the same time. So therefore, for the smaller frequency, there will be obviously more points per cycle. Therefore, the condition is automatically satisfied. That is why you choose the largest frequency for determining the sampling rate. Okay, so you have points in between accordingly adjusted. So all the points are collected in your total FID. The total number of points which you collect from here to here then determines your acquisition time. So now it's equal to 1 by 2 times tau max. Okay. So if you have so much number of frequencies, omega max is this, and you have all other waves which are smaller. So for each one of those, obviously, there will be more than 2 points per cycle. Therefore, that dwell time is selected on the basis of the largest frequency. Okay. Folding of signals. This is the crucial point. Often you see this is very special to Fourier transform NMR. This does not happen in the case of CWNMR. This is very special to Fourier transform NMR. Here the digitization theorem comes into the picture. Okay, the sampling theorem poses a difficulty that one has to know the frequency range in the spectrum, even before collecting the data. How much spectral width you should give? What is the largest frequency you have to give? Because you don't know a priori. What is the spectral range? How to decide this, omega max? Okay, trial and error one can do. You can choose a very largest spectral width to begin with, and so that you collect. But then, of course, you run the risk of not exciting all of them properly. All the things may not be excited appropriately. Therefore, you may miss the signals which are there actually, but you may miss them. So, therefore, there's a difficulty there. So, you choose in some way. Then there is, of course, a possibility that you make a mistake. The mistake of choosing the offset with regard to the spectral width can be a problem. So let us see the situation here. Here is the spectral range from here to here. This between the two black lines. This is the spectral range you have given, and accordingly you have kept your offset in the middle here, and you are doing quadrature detection. So in your sample, you have the frequencies here which are on this side as well on this side. Let's call this as positive frequencies, and these are negative frequencies which are present, and quadrature detection is able to select this. Okay. Now, it so happens that you have not chosen the spectral width properly. You chose the spectral width from here to here, but there is a signal which is present here. You did not know this because you made a mistake. You made a mistake. You ought to have chosen this frequency. Omega max has to have included this, but you did not include this. So what will happen then? So this fellow will fold over to this point. The signal will come over to this, giving an impression that there is a frequency here in your spectrum. Although if you look at it very carefully, this signal will appear with a different phase. It will have some funny phases there. You can detect that, okay, this is a folded signal. But nevertheless, if you are not careful about that, then you start thinking there is a frequency here, which is wrong. So this is called as a folding. So the peak folded with the distorted line shape, peak outside the spectral region. So this is the peak which is folded with the distorted line shape, and this is the peak which is outside the spectral region. You did not choose your spectral width properly and the offset properly, and because of that, you got this signal folded over onto this. Okay. Now, let's try and understand why this happens. How does this happen? There is where the digitization theorem comes into the picture. I told you earlier that Fourier transformation of the digitized spectrum generates a whole range of spectra. So many sets of f of w are coming in. So you have from here to here is one f of w, from here to here is another f of w, from here to here is another f of w. Okay, and then of course you can go on, another one here and another one here. So a whole lot of spectra are generated by this sort of a situation. Now what happens here? Suppose I have a signal in the previous as considered. I chose the spectral width from here to here, and I had a line there. I had a line here which I did not include. But it will get excited, it will get Fourier transform. And then it will show up here from this point, it will show up as a signal here. Right? From this side, because this is a positive negative frequency. The f of w is from here. Now the spectral region which is coming from here, it will produce a signal here because that is the same here. That is the same here. From this spectral f of w, that signal is appearing here. Okay. And from this one, it will appear here. From m+1 region, it will appear here. This one which is coming, which is outside of n of 0, and that will appear here in the n is equal to 0 area. It will appear here in the n is equal to +1 area. But you filter this out, you filter all of these out, and you keep only this one there. Okay, now we see why this is coming here. This is actually coming from here. This is actually coming from this f of w, the one which is next neighboring to it. From that f of w, it is producing the signal at this point. But all kinds of filtering which has happened, that is distort the phase of the signal, and that's why you get a frequency at this point. Similar things will happen when you do single channel detection. In that case, of course, it will appear on this side. We need not, the same arguments will hold good there as well. Okay, so therefore you get a folded signal in this. This is the consequence of digitization and Fourier transformation of the digitized FID. Okay, now the next point is phase correction. This is again very special to Fourier transform NMR. And we said earlier that if I have a function FID which is like this, do a cosine FT, I get an absorptive signal like this. If I have a sine function, and what is this here? This is because of the decay, exponential decay. This signal is decaying as a function of time, and this is exponential decay. This is the first order process. When there is a first order process, you have a single exponential contribution to the decay process. So here again, it is a single order, first order process. It is a single exponential decay, and it produces a dispersive signal in this manner. Okay, this is perfect spectrum. If it is like this, absolutely no problem. But you don't get like this. What do you get? You get very different kinds of distortions in the phase of the signal. Why does that happen? The first reason why it can happen is the improper phase of the RF pulse. So the RF pulse, instead of bringing the magnetization, the initial magnetization is here, the 90x pulse, let us say, or minus x or whatever, is supposed to bring the magnetization to this point exactly along Y, but it does a mistake and it brings it here. That means you are not applied a pulse along the x-axis, but along a slightly away x prime axis in the transverse plane, but not aligned with this. What does that mean? This means that there is a phase difference with respect to the receiver. We said with respect to the receiver, if the transmitter's phase and the receiver phase are identical, then we say it is X, or if it is 90-degree phase, that is Y, and so on and so forth. But if this phase is not properly maintained, then it will appear as an error. So therefore, the phase of the RF pulse, it is slightly different from what it should be with respect to the receiver. Therefore, it will appear as if it is along the X prime axis. When it is along the X prime axis, magnetization does not come along the Y, but it comes at this point. Okay, so therefore there is a small angle theta here. So let us say now, what will be the component of the signal? Suppose I collect my detector is kept here. Detector is here. So what is the component of the signal along the y-axis? Component of the signal on the y-axis, you add the theta here, omega it plus theta. The additional phase is added. Additional phase is added to the signal. And then of course it will decay as e to the minus at. So therefore signal will be e to the minus at cosine omega t plus theta. Okay. What is the consequence of this? Now I take a Fourier transformation of this cosine omega it. So you see now what is the expansion of this? Okay. So let me write this e to the minus at See, therefore, you see, it has two components there. It has a cosine component and a sine component. The cosine component produces an absorptive signal. The sine component produces a dispersive signal. And they are weighted. Cosine component is multiplied with the cosine theta, and the sine component is multiplied with the sine theta. So, depending upon the theta value, you have different admixtures of the cosine and the sine components. This will result in real and dispersive things. So therefore, Fourier transformation of the cosine dependent FID leads to real and imaginary parts, both of which have absorptive A and dispersive decon. This is what I said. The cosine part will give you the absorptive, the sine will give you dispersive. So suppose I want to write that as, I remember this is only the cosine part collected, the real component collected. Similarly, if I collect the sine component, that will also have the same feature. So when I write this is the cosine real part, and what I'm referring to here is the real part. The real part of the signal will have both an absorptive component and a dispersive component, and they are weighted by cosine theta and sine theta. Similarly, the imaginary component, that is if I collect the sine part of the signal, sine omega it plus theta, if I collect that one, then it will also produce a dispersive component and an absorptive component, which is weighted by cosine theta and sine theta respectively. So the absorptive signal will look like this, and the dispersive signal which will look like this. And where does the dispersive signal appear? In the real Fourier transformation, half the data points which I mentioned, they are for the real part and the half data points are for the imaginary part. Half data points are used to represent this spectrum, half data points are used to represent this spectrum. We need to store both of these. And both of them have admixtures of both absorptive and dispersive components. Okay, so this is what happens when you have improper phase of the RF pulse, and this will be dependent on the theta value. Theta, if it is 0, of course you will have the pure absorptive signal. If theta is equal to 0, then of course you only have A. The D part is 0. Similarly, the imaginary one, if theta is equal to 0, you only have dispersive component, absorptive component is 0. But when theta is not 0, then there is the error in the phase of the RF. Then you will have this kind of a mixture of this. And this will be true for all the signals in the spectrum. Not only one is not frequency dependent. This has to do with the initial phase of the signal. At the time point 0, what is the initial phase? See, it is dependent on, therefore this is called as the zero order phase. It is not dependent on the frequency, but it is a zero order phase. So, and that will reflect in this kind of a admixture of the real and imaginary components. And you see, this is what you get from this pure absorptive signal. Then you see here, this is the kind of a spectrum what you will get. Okay, zero order phase. Now, with zero order phase error, now you could do a proper phase. Now, how do you collect? How do you phase correct it? You need to collect both the real part and the imaginary parts. Okay, now let's see that here. So you collect, this is the real part and the imaginary part of your Fourier transform spectrum. You multiply this as indicated here. You multiply A by R cosine, R you multiply by cosine theta. R is multiplied by cosine theta and I is multiplied by sine theta. You do this operation. You need to have both of these. R you multiply by cosine theta, what do you get? A cosine square theta minus D sine theta cos theta. Okay, and then you multiply the imaginary part by sine theta, what do you get? D cosine theta, D cosine square theta plus A sine theta. So what did I say? Multiply by sine theta. So D cos theta sine theta and A sine square theta, right? So now if you add these two, this portion will cancel. D cosine theta sine theta, and from here the D sine theta cosine theta, they will cancel. And that is what will happen here. If you R cos theta plus I sine theta, if you see, the dispersive component gets cancelled and you will get a pure absorptive signal. Okay, that is the phase correction here. When you do this with the proper phase, and this determine, how do you determine theta? This is typically done by trial and error. The value is determined by continuously by varying it. A priori, you do not know how much it is, but it keeps, this is the on the fly, you can do this. You can change, the computer is coded to that way. You continuously change that theta so that you get a clean phase here. And you can look at it from the baseline. The baseline should remain flat all through. And that is an indication that you have a good phase. Okay, now there is a second source of error in the phase, and this is delay in start of data acquisition. First order, this is called as the first order phase error. Why does that happen? So this again comes from your the Fourier transformation artifact. Okay, now you supposed to start the data collection from t is equal to 0. Okay, t is equal to 0, and but there is you always have a small delay, delta t I wrote earlier in the EW t plus delta t. Now here I represent this capital delta here. So there is a small delay in data acquisition. You are supposed to start data acquisition from here, but you start data acquisition from this point. So that is a small delay there. Okay, that is delta. This delta, a consequence of that is, suppose delta were 0, your magnetization would have come to this point. Okay, if delta is not 0, now we remember this is the superposition of all the frequencies. This is the summation of all the frequencies, right? Summation of all, summation of cosine omega i's, cosine omega i's, right? Now, if delta is not 0, then what happens to this? These different frequencies will start processing. During this period delta, they would have moved to different extents. So when they move to different extents, they all have different components along the y-axis. Therefore, they will have different signals. During the time delta, different spins acquire different phases in the transverse plane. This leads to different degrees of admixtures of absorptive and dispersive signals for different spins. As I said in the previous case, if all of them acquire the same phase, yeah, there is a phase error, all right, but it is the same for all of them. But here they acquire different phases. Different ones will acquire different phases. Therefore, this becomes a frequency-dependent error, the frequency-dependent phase, and that is called as the first-order phase error. You can see that here now, as you go from left to right, the phase error is increasing through the spectrum. So all along from here to here, as you go further away from your acquisition here, that is, this is the low frequency, high frequency, and things like that. It is going. Then you have the phase error is increasing. This is the first order phase error. Now this requires a little bit of mathematics and algebra to see how one can correct this. So let us look at this. You have a delay in your data. I'm sorry, I'm using different symbols at different times. So here is T naught. Previously, I put a delta. Again, earlier I put a delta T. But you may be clear about it. What I'm trying to refer. So yes, let us say my signal is ST plus T naught. This is the delay. This is the delay. So Fourier transformation will add additional phase here, e to the I omega T naught f of w. This we saw earlier. This is the digitization, the delayed acquisition. In the absence of the delay, the f of w is of course a mixture of real and imaginary components. I can represent this as modulus of f of w, f of omega, and a phase. So this typically you can write it as a phase, right? So this is you want to represent the diagram. So if your f of w is here, so this is the real part and this is the imaginary part, and you have a phase here, phi. So, and this is your main signal, f of w, as a vector picture if you want to give. So this is the phase of your spectrum, where phi is the phase and amplitude is f of omega. This is square root of the r omega square plus r omega square. So this is pretty straightforward. And tan phi is r omega by r omega, because this will take a slope here. That's the tan phi. So this by this is the tan phi. Okay. Now, as a result of shift of origin in the FID, the modified spectrum f dash omega will be f dash omega is equal to e to the I omega t naught f of omega, because this is what is the consequence of the delay. So this will again give me a kind of a phase which is phi plus omega t naught. Whatever was, phi is the phase, but this is additional phase. So therefore, I have a total of phi plus I omega t naught. So this is the total phase.
This T naught is equal to delta.
D naught equal to delta. Yeah. Remember, this phi here includes already an I. Okay, this is already represented as a phase. This includes an already phase. If I want to take out that phase, then I will have to take out this I out and then put a phi plus omega, but it doesn't matter. So this is the total phase. Okay. In principle, I can do that also here. You can say this is equal to e to the I phi plus omega t naught. To say that, to separate that out clearly. Okay. So then f of omega, this is the phase. Phi plus omega t naught is the phase, and I contributes to that complex factor. Maybe we should correct this. I think we'll try and correct this also in the end. In this. Put I out and put phi plus omega t naught. And this will give you r dash omega plus I dash omega. And where r dash omega and I dash omega are the new real and imaginary parts. Now here I represented the time phase as phi is equal to phi plus omega t naught. So therefore, that is the same thing as what is written there. And this is I dash omega by r dash omega. Okay. So now r dash omega is f of omega cosine the phi plus omega t naught. Okay. So that is the real part. And where does this one come from? This comes from the expansion of e to the I omega t naught plus phi, right? So the cosine omega t naught plus, you expand this here. You expand this, you get cosine phi cosine omega t naught minus sine phi sine omega t naught. So let us put a, there is one more thing which is missing here. I should put a bracket here. Should put a bracket here. F of omega multiplies this whole thing. Okay. So therefore, this is equal to e to the cosine omega t naught r omega minus sine omega t naught I omega. Where does this come from? This comes from this expansion itself. This is the product is cosine omega t naught plus I sine omega t naught multiplied by r of omega plus I of omega. Okay, and when you multiply this, you will get the real component and an imaginary component, and that is what is represented here. We are talking about the real component. The real component is cosine omega t naught r omega minus sine omega t naught I omega. So this similar thing will apply for the imaginary component as well. Now, if omega t naught is extremely small or far less than 1, because the t naught is a very small number, typically it is about 100 microseconds or sometimes even less than that. So if omega t naught is a very small number for the whole range of the frequencies, then e to the I omega t naught can be expanded up to first order in omega. Okay, what is the expansion of e to the I omega t naught? E to the I omega t naught is equal to 1 plus I omega t naught plus 1 by 2 to real I omega t naught square and so on. This is the expansion of the e to the I omega t naught, right? Now, if omega t naught is very small, we ignore these higher orders and keep only the first order one. So then we write f dash omega is simply equal to 1 plus I omega t naught into f of omega, and that is relating to this expansion here, this expression. F dash omega is 1 plus I omega t naught into f of omega. Okay, now therefore we have written this r dash omega is r omega minus omega t naught I omega naught, and I dash omega is I omega plus omega t naught r omega. Therefore, you combine these two here to make this little algebra there, you get that r omega from here, the solving these two equations, from these two equations, if I make this calculation, r dash omega plus omega t naught I dash omega, that is, I keep this as it is, multiply this by omega t naught and add that there. When you add that, you get r omega into 1 plus omega t naught square. So therefore, r omega is equal to r dash omega plus omega t naught I dash omega divided by 1 plus omega t naught whole square. Under the condition omega t naught square is much less than 1, we can ignore this in the denominator. So we can simply say this is equal to 1. The denominator is simply equal to 1, because you can put this number very small. So how do you know that? Let us say this omega is, what is the range of your omega? Omega is in the order of kilohertz. Let's say 10 to the power 3 or 10 to the power 5 into 10 or 1000 hertz. 1000 hertz is 10 to the power 3. So, and t naught is of the order of microseconds, and therefore it is 10 to the minus 6. Therefore, this number is extremely small. And when that is the condition satisfied, then you can ignore the square part there in the denominator, compare it to 1. Therefore, you can write r omega is equal to r dash omega plus omega t naught I dash omega. Now you see the calculation is somewhat simpler because it is linearly dependent on omega. The phase correction is linearly dependent. How much phase to be added is linearly dependent on that. How much to add mix? What it means that to get this pure r omega, we have to mix the real and the imaginary components of the spectra by appropriately weighting them. So the weighting is r, the real part is taken as it is, the imaginary part is multiplied by omega t naught, and this multiplicative factor is dependent on the frequency. But fortunately now under this condition, it is linearly dependent on the frequency, and therefore it is easier to do for all of them, for all of the frequencies. And when you do that, you will get a pure phase spectrum. So that is so much for the phase correction. So we have the clean spectra, zero order phase and the first order phase. Oh. Should we take a break here?
Yes.
5 o'clock. How many more slides are there?
इसको ऐड कर दो लेकिन.
Oh, thoda sa, okay, we'll give a break for 5 minutes, 10 minutes.
Yeah, we'll start after 10 minutes.
So in the meantime, you make those corrections, huh?
तो slides में जा.
Slides में वो correction करते हैं.
Back करो.
Yeah. Okay, you can close this. Mike, you can close.
Connected, na?
Hmm. Okay, so let us start again, continue from where we stopped. And this is the next feature which is very special to FTNMR. Of course, FTNMR means, as I said, FTNMR is the basis for all high profile NMR, 2-dimensional, 3-dimensional. For everything, this is the fundamental. FTNMR is the basis of all of those ones. So whatever we discuss here is applicable to all other dimensional NMR as well, 2D, 3D, everything it is applicable there. So the dynamic range is a very special problem with dealing with FTNMR. It did not exist with the CWNMR. What is the problem here? So dynamic, this, as we said, the data is collected in the digitized form, but as it comes out of the sample, it is not digitized. It is in an analog signal. It is coming out as an analog signal, and somebody will collect it and digitize it. And there is a device for that which is known as the analog to digital converter, and that is called as the ADC. ADC converts the signal that comes in the digital form. The digital form is, it is represented in the kind of a binary number. Okay, the binary. Let us consider that you have a 4-bit analog to digital converter. So 4-bit is, now how do you all understand what the binary number is? So if I have a 4-bit ADC and I suppose I fill all of them, see in each of these, this AGD there can be only 2 numbers, 0 or 1. Binary means either 0 or 1. Only 2 possibilities are there. Now if this is 0, there is no this thing. If it is 1, it is full. So let us assume that they are 4-bit ADC and it is full, and all the 4 bits in this one are 1111. So what is the number which it represents? This represents the number 2 to the power 4 minus 1, because you see this one is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So all of these add together, it gives you the number 2 to the power 4 minus 1, that is equal to 15. Now, if you have a number which is greater than 15, then it cannot, the 4-bit ADC cannot represent it. Okay, since each point in FID is the sum of all the signals in the spectrum, the total has to be less than 15. Then if there are 2 signals with an intensity ratio of greater than 15, the smaller signal will not be represented in the ADC at all. The signal will be lost because the largest signal will already fill it. So the ADC will be full. There is no room for the smaller signal in the digitizer. Therefore, that signal will be lost. So this is called as the dynamic range problem. Now, typically, what one does is, what are the kinds of digitizers we have? These are hardware units. Remember, these are hardware units, and the digitizer converts the analog signal into the digital form. And you can have digitizers of different resolutions. Then there are typically 12 to 16-bit ADCs are used in modern spectrometers. 12-bit ADC or 16-bit ADC. Or you can say, why not I go to larger numbers? I go to 24, 32. Can I go to larger and larger ADCs? No, you cannot go to much larger ADCs because it will increase the noise. The digitization process also introduces noise in your signal. Therefore, you cannot go to very high resolution ADC. Typically use 12 to 16-bit ADC in modern spectrometers. Now, suppose I have a 12-bit ADC. The largest number it can represent is 2 to the power 12 minus 1, that is 4095. If 1 bit is used to represent the sign, because you need to represent the sign also, whether the signal is positive or negative, then you say I reserve 1 bit to say, okay, this signal is positive or negative. That means if it is 0, it is positive, if it is 1, it is negative, and so on and so forth. Then I will only have 11 bits. If I have 11 bits, the number which I can represent is 2047. So now, suppose I have a solution of 1 millimolar of a solute in water, in pure water. The proton concentration is 110 molar, right? So this is H2O. H2O is 110 molar. Then if I have a sample which is 1 millimolar, then what is the concentration intensity ratio of the 2 signals? Because all the signals will come together. They will all be overlapping, and FID will collect all of those. 110 molar divided by 1 millimolar, that is 1.1 into 10 to the power 5. So this is far above what you can represent in the 12-bit ADC. So it is 2047 only, right? If you have this large ratio, no matter how much you scale it down, you may scale down the whole thing by a certain factor, but still you cannot recover the small one because the ratio is much more than 2047. So long as the ratio is less than 2047, you can recover it by scaling down and fill it up in the ADC and things like that. So that is, if this is the case, then you will not be able to collect the solute signal at all. the cellular signal will not be registered in the ADC. This necessitates designing of techniques for suppression of strong solvent signals. Presence of such strong signals leads to further overloading of receivers as well. And that is indicated here. So if you have overloading of the receiver, everything is full, you have much more, then of course you generate a flat thing on the top. It is not, the signal is not being represented properly at all. And then you have this water signal and it results in a small, it is a distortion of the phase here like this. And your compound signal, it looks very tiny like this, even if it is represented properly. Even the signal is represented properly, the overloading of the signal can, overloading the receiver can produce the distortions of the line shapes in your signal. So first problem is, then you have to have a signal, the ratio which is less than what can be represented in the digitizer. Secondly, you cannot adjust the gain of your receiver so much that it will overload the ADC, overload the receiver. So therefore, when you do this, then you generate distortions of your signal. This is the gain factor which is complex and which has to be adjusted, optimized. So you have, therefore there are various schemes which are generated to suppress the water signal in the spectrum. This have been discussed earlier, Watergate and things like that. We discussed it when we were talking about the gradients, use of the gradients to suppress the water signal. We talked about that. And the reason for that is as this, what we indicated here. Now, next is the cosmetics. Data processing to improve the NMR spectra. I'll take you back to the convolution theorem which I mentioned earlier. How is that going to be useful? How we can improve the appearance of the spectrum? And this is the number of data points in the FID is restricted by signal to noise considerations. What do I mean by that? So if I collect the FID like this, okay, now depending upon the number of data points I have, n times, let us say the 12 time dW is equal to the acquisition time. Okay, and the signal is decaying like this. Suppose I keep on collecting data beyond this to increase the acquisition time, to increase the resolution in the spectrum, because the resolution is inversely proportional to the acquisition time. So if you keep on collecting the data more and more like that, then what I'm collecting? I increase the acquisition time, all right, but then I'm collecting only noise after that. So therefore, you generate a lot of noise to increase the number of points, to increase the acquisition time, you added noise, and that will destroy your spectrum. Signal to noise ratio will be poor. Therefore, you cannot increase the length of the FID, you cannot increase the number of data points arbitrarily. So what do you do? However, we need larger number of data points. So what do we do? This is done by what is called as zero filling. So you add artificially points. So this is a truncated FID without zero filling, and you generate a spectrum, Fourier transform it, and then you see you have this truncation here, right? It's like a step function. When you have a step function in your FID, when you Fourier transform it, then you generate the sync distortions in your spectrum. See all these kind of things which are there, wiggles in the baseline, you will get them as a result of this kind of a truncation error. Now, if you can increase the number, that is number one, and you can increase the number of points, truncated FID with zero filling. Now, to increase the number of data points, you put in lots of zeros here. Okay, so here there were no points added. Here, what you have done, you added from here to here these many points to increase the number of data points. Okay, as I said here, to increase the number of data points, to collect more points, then you will have a higher resolution, but a poor signal to noise ratio. You cannot do that. So therefore, in order to improve that, what you do, you add zeros. The FID is here, truncated here, FID is finished there, but you add these many zeros. Okay, you certainly have increased the number of data points. Okay, but when you do Fourier transformation, of course, this problem is not gotten over, but you certainly increase the resolution in the spectrum because you have put more points there. The data is represented better. See, this triplet is looking better, this doublet is looking better than this is looking better than this. So this is improved here with regard to the resolution in the spectrum, but the distortion in the baseline is not gone. See here, this is a distortion in the baseline, and that is the result of the truncated FID. Okay, because there is a sudden step function. It suddenly drops down to zero, and you are putting zeros there. And the consequence of this is all these sync modulations here in your NMR spectrum. So how do we do this? How do we get over this problem? This is done by digital filtration or window multiplication, or it is also called as apodization. When the FID is truncated and zeros are added, FT of the FID leads to serious distortion due to the sink. Sin x by x wiggles appearing on either side of your line. This is what I showed earlier. So here also you see this is more blown up picture of the same. This is the previous one only, but this is more blown up here with zero filling. Now you do this one here with exponential multiplication. This is the manipulation what we are doing. The FID is the same, but we multiply this by a function e to the power minus t by something. It's an exponential multiplication. Instead of after the truncation is there, you multiply this by a certain exponential function. You see this is now exponentially decaying down to zero. It is coming down to zero here. There is no sudden truncation there. So truncated FID with the zero filling and exponential multiplication. Okay, this is like convolution. So you are doing convolution to smoothing of the data. So you do the smoothing of the data, you get this. But this is done in the time domain by multiplying your FID with the exponential function. Okay, truncated FID with the zero filling and exponential multiplication. If you do Fourier transformation, these wiggles are gone. However, you also pay a price. The price you pay is lines get broadened by an amount 1 by pi times T max, and the resultant line width will be given by delta nu is equal to T2 star plus T max divided by pi T2 star T max. This one can calculate it, but this is the result what you get. So you pay a price in terms of the spectral resolution. You get a good looking spectrum, you have to remove all these wiggles in the baseline, but you can generate a enhanced line width. So you pay the price by exponential multiplication. So this is not completely suitable, so you should do something better than this. And that is, this part, the top portion is the same everywhere. Huh? So this is for comparison, I'm keeping that. Now instead of exponential multiplication, you multiply by this function. It's a cosine function. The cosine function pi t divided by 2 times t max. So what is this function? This function you see here, when t is equal to t max, it is a cosine function. When t is equal to t max, it is cosine pi by 2, right? Cosine pi by 2 is 0. Therefore, at the last data point, this window function comes down to 0. So it is a function which is like this, is a cosine function, and it comes down to 0 at your FID. The FID is going like this, it exactly comes down to 0. Therefore, there is no sudden truncation, there is no sudden what we call the step function in this procedure. So the FID will look like this only. FID will look like this, and then it is coming to 0 at the last data points. And that is when t is equal to t max, you are getting cosine pi by 2. Other than that, it is a cosine function which is like this. So when you do this, now you see what is the result here. You have not lost the resolution. Resolution is kept, but the lines also are very looking beautiful. All the sync modulations are gone. So this is the cosine modulation. You can do cosine multiplication, and this is done in the time domain. This smoothing, as I said, this is the convolution. The smoothing operation which is done is done in the time domain, which is easier to do. The multiplication in the time domain is easier to do, and therefore this is the cosine function. Therefore, I call this as cosmetics. This is the data collection is one thing. After that, the data processing becomes an important factor to obtain a good NMR spectrum. Okay, now you can do all other kinds of manipulations as well. You can do sine Bell functions. The sine Bell function is like this: lambda t sine phi plus pi t by t max. So what does this mean? So suppose t is equal to t max, then it gives sine phi plus pi by 2. Sine phi plus pi by 2 is cosine phi. So this is the kind of a phase shift. If phi is equal to 0, then you have cosine phi. But if phi is not 0, then of course you will have some other kind of a distortion. With the zero filling and sine Bell function, and this is pi by 2 is 1, phi is equal to 0, then sin pi by 2 is 1, right? So what time t is equal to 0, what it will be is sine phi. And that is if phi is equal to 0, this initial point will become 0. Suppose the FID is going like this, right? So let us say t is equal to 0, that is the first data point. and phi is equal to 0, then this whole function is 0, therefore initial point becomes 0. So if your phi is equal to 30, there is a kind of a phase shift of 30 degrees, then initial point is not 0, but it is you take 30 degrees phase from there and it is multiplied by there. And at, of course, at last data points, it also comes down to 0. So the FID, the sine function is like this, right? So either you start multiply from here or multiply from here or multiply from here or multiply from here. If you multiply from here corresponding to this is a cosine function. If you multiply from here, it is a sine function. If you multiply from here, then it is a phi is equal to 30 degree. Multiply here, phi is equal to 60 degrees. It's a kind of a phase shift. So phi is equal to 90 is like a cosine function. This is the same as what we had in the previous case. Phi is equal to 90 is a cosine function. So therefore, by doing this, what we get? If you multiply by this here, phi is equal to 0, see the result is you get extraordinary resolution you multiplied. Very high resolution you get in the multiplied. But then of course you get this wiggles here. The negative, positive, negative wiggles you get here in this each one of those. But the resolution is extraordinarily high. So you look at this triplet, how it is looking very all the way down to the baseline.
Having problem connecting to the network. Sir.
Who is having problem?
Lost connection, the students.
Oh.
Came.
Okay. Vishal? कनेक्टिविटी लॉस
तो वाला कनेक्टिविटी का प्रॉब्लम देखो तो स्टूडेंट्स का भी रिमूव है लॉस द कनेक्टिविटी
नो सर
देखो एक बार है ना ओके सर
Is okay? That may be temporary. Temporarily, net there is a problem in their place.
सकता है उनका पोजीशन में गड़बड़ हो सकता है
It's okay, let's try it once.
यस यू कैन कंटिन्यू
Okay, okay. So this is how by this function, this represents all of this. You have the various possibilities of improving the resolution and improving the shape of the spectrum. So you can optimize this. How much resolution you want with regard to how much distortion you can tolerate. If you want to measure the coupling constant, for example, surely you want a very high resolution there. So that you can measure the separations much better. But if you want to have, not interested in that part, but you want to get a good baseline presentable spectrum, then of course you typically can use phi is equal to 90. Often one uses phi is equal to 60, which is a compromise between both these situations. You have a good baseline as well as a good resolution in your spectrum. And there is a Lorentz-Gauss also. This is a little bit more complicated spectrum. This of course performs very well. And this is the spectrum which is multiplicative factor is this e to the t by t2 star minus sigma square t2 square by 2. Sigma is a parameter which has to be adjusted for a given t max and an estimated t2 star. So a priori you need to know some values of this, and accordingly one can use this also. So often by and large one uses sine function or the cosine functions, or sometimes one uses the sine square function also. Okay, so that finishes this part. So now we move on to the, so this typically now the instrumental facts are finished. Instrumental part discussion is finished. Now we go to the analysis part, some analysis part. In the next one, I think we are taking up the analysis. Actually, Sunil Ghosh can do a much.
Yeah, that I'll cover some of them, but at least you to be clean.
Yeah, so here you see. This is on this one spectrum alone, you can spend the whole hour.
Yeah, that is.
But I will only illustrate some points here, and then we can go on. See, this is the molecule. Now we are going to talk about some analysis part. How to use the different kinds of spectra for analyzing it. Okay. Now here is a complex molecule. How many protons are there in this? Let's try and go through this spectra a little bit more carefully in detail. How many more protons are there here? So you see there is a 12, number 12, but there are multiple doubles in many cases. You have the 8, 8 prime and 8A, 9, 5A, 5 prime, 5 double prime, 4 prime, 7 and 7 prime. So and then of course you have the methyls. methyls on the sides. And these ones are the oxygens there. So there is, and then what we have here is the double quantum. Their assignments are also indicated on the top. Individual assignments are already given there, but typically these are obtained after this analysis. These assignments are obtained after the analysis, but to understand these assignments are already given on the top. Let us take, and then of course these are phase sensitive spectra. You can see the double quantum filtered COSY, the blue and the red indicate the positive and the negative components. Okay, so these are high resolution spectra, very well resolved spectra, and you can see the fine structures in the individual peaks as well. Okay, let us take a particular example there. Let us take number 9. This is peak number, this is proton number 9. Proton number 9 is here. Okay, and what is it connected to? In the double quantum filtered COSY, what we see direct correlations, direct J coupling correlations we see. Okay, and what is it connected to? The proton number 9 is this. It is connected to this methyl. Okay, where is that methyl? That methyl is here. Number 9 is connected to the methyl there. The very fact that it is appearing in this high ppm range, it tells you that okay, it is a methyl. And that methyl is a nice peak here, you can see that is a methyl there. And that's why these horizontal and vertical lines are also drawn there, so that you connect these appropriately. You have the double quantum filtered COSY on the top, then you have the TOXY at the bottom, and then you also have the NOSY here. And horizontal and vertical and the green lines are drawn precisely to be able to make a connection from those. From all the way from top to the bottom here, you can see the lines are running. So this, one can sit down with these spectra and analyze each one of these peak connections. How they are made. You can understand that. We will see some of those there. So the 9-1 is very clear. 9-1 is showing you two connections. One to here, the methyl, and that is this one there. And then you have connection to this point here, and that is 8A. 8A is this. It is showing connection to this in the double quantum filtered COSY, and it is not showing to anything else. Therefore, there are only two peaks there, two cross peaks there. Similarly on that side. Now let us look at some other one. Which one is this?
Four
This
double prime.
4
double prime is having
4 double prime. Let's look at the 4 double prime. This is showing two peaks again. 4 double prime is showing to 4 prime. Where is 4 double prime? 4 double prime is here, and it is showing to 4 prime. 4 double prime to 4 prime. Then it is also showing to this one here, and this is the 5 double prime, 5A or 5 double, which one is that? 5 double prime, which is showing to 5 double prime. It is also, it doesn't show to 5A. This is a 5A.
five prime and it should be 5 prime and 5 double prime, both there in the same.
Both are there at the same place.
Yeah, it is there.
Oh, 5 prime is here.
Yeah. 5 prime is there and 5 double prime is very close.
So 4 double prime is showing to 4 prime also. Where is 4 prime? 4 prime is here only.
Yeah.
4 double prime to 4 prime, and it is also showing to this one here, 5 double prime. It's not showing to 5 prime though. The 5 prime is here. It should have been here. That peak is not same. So that coupling is small. Coupling is small.
Very small, yes.
So because the coupling is small, there's the positive negative things are cancelled out. So you don't see that peak. So
The
therefore,
angle is 90 degree.
right.
And it's becoming very close to 0.
Exactly. So therefore, you are not seeing that one there. Now let's look at the 5 prime. The 5 prime is here. The 5 prime is showing to 4 double prime. Where is the 5 prime? 5 prime is showing to 4 double prime. That is here. And 5 prime is showing to 4 prime, rather weak.
Yeah.
Rather weak. That was the same thing here, what we saw. It did not show. 5 prime to 4 prime, rather weak. And 5 prime shows also to this fellow here, to 5A. It shows to 5A here. Huh? No, 5A is here.
Yes, it will be showing because
It will be shown to 5A. Okay. So let us look at the toxic spectrum. So this is how this one is showing all direct connectivities. Okay. Double quantum filtered COSY is showing only direct connectivities. Let's go to the toxic. Now, what does the toxic tell you? Let's look at 9. Once more. 9 is showing to what we saw, 9 is showing to 8A, 9 is showing to 8A. See, these red arrows are basically indicative of the NOE connectivity is there. NOE connectivity, the red arrows there. Okay. Let's look at the toxi. Toxi is showing 9 to 8A, and of course to the methyl, 9 to the methyl. It will show that there's the direct peaks, there is the double counterfiltered COSY. But you see also two little peaks here. And which one is that? That one is 8 prime. 8 prime, it is showing from 9 to 8 prime. How does that come? That is a toxi effect. That is a relay. Okay, so there is no direct coupling from 9 to 8 prime, but it is 9 to 8A and 8A to 8 prime. Okay, so if you obtain any other coupling information, it should match with this. Okay, so you get a little one here, which is to the 8 prime. You also get one small one here, and that is to 8 double prime. You see, go this vertical line there, 8 double prime. So 8A to 8 double prime. So you are seeing 9 to 8A direct peak and the relay peak to 8 prime and 8 double prime. Okay. So let's do the same thing for the 4 prime. Now if you look at the 4 prime, the 4 prime was showing you two peaks there. We show one peak here, this is the 4, what we say, 4 double prime you're looking at. 4 double prime was showing peak to 4 prime and also to this 5 prime there. Now you see, you are seeing more here. So 4 prime, you are seeing to the 4 prime as before. You are seeing to the 5 prime. You are also seeing to this one there. This one is 6. That is 6. Okay.
Yeah.
Where is 6? 6 is here.
By far.
Is far. So therefore it is a relay.
Yeah.
Is the relay to the 5A? It is showing to the 5A also, right? This is 5A. So therefore from 4 double prime to 4 prime, then there is a relay from here to here, here to here, here to here, here to here. So there is a relay. So 4 double prime you are seeing to 4 prime, then to the 5 prime, then this one is the strong one, which is this one there. This is the 5 double prime. 5 double prime is showing a strong one, and then from 5 double prime is showing to 6 and to 5, and then of course is also showing to this one there. Which one is this? But that is not labeled. That proton is not labeled. This first one there.
That is it 0 ppm? PMS?
No, it's not at 0 ppm.
That has not been,
It is a single. That is not a sign there.
yeah, that is a,
And it is showing to that also, which could be that. So there is that could be, all others are assigned. Anything is missing here in this?
see, that peak is almost connected to almost all peaks. See.
Yeah, that was connected to almost all of them.
That must be,
Which one is that? That's an interesting one. The 12 is missing in this line. In the top ones, see 12 number is missing.
but 12 will not come there. 12 will connected to oxygen, na? So.
12 is this, 12 is connected to oxygen. So it is some sort of a methyl it is.
Yeah, that looks like a methyl. That's why I'm telling that.
Yeah.
And I think it looks like that it is around 0 ppm.
Yeah,
0 nahi, this will be around 0.8 or.
it is around 0.8. So 1.5, so 1.1, 2, 3, 4, 5. So it is around 0.9.
So one of those methyls, na?
Yeah.
The methyl which is connected to carbon 6.
I guess so.
Yeah.
So I think this methyl which is connected to the proton 6 here
Yeah.
and is showing this all these relays.
Yes, yes. Yes.
It's so many relays
Yeah, it is showing relate to almost all.
to all of them. 7 prime, 8 prime, then also to the 5 prime, 5 double prime, 5A, 5, then also to this one, 6. Yeah, it is in this area only.
Yeah, I think so that.
It is this
methyl
methyl.
refers to, yes.
This methyl. Yeah. You see, this is how we can do the analysis. I assign the individual resonances on the basis of the toxic spectrum is so useful here. And in this case, the correlation was shown to this only. In the double quantum filtered COSY, you show correlation only to this. Yeah, you see here. It showed only to the 6 there.
Yes.
But of course, you could not figure out that whether the 6 is this is the methyl or not,
Yes.
because 6 can be connected to many other things.
Yes.
But this will actually show the whole relay. Of course, the chemical strip will tell you it is like a methyl. This whole thing is relay. Okay, so that is the toxic variant. Now let's look at the NOE part here. Now NOE, notice one thing here. In the NOE, you have the blue and the red signals. And why are these? Because the NOEs have negative signs. For small molecules, the NOEs have opposite sign compared to the diagonal. And that is why you see opposite signs there. Now you see this methyl here. Methyl is showing NOE to 7 double prime, 5A, 6, 7 double prime, and 5. So all of these are short distances. So okay, all these you can measure these intensities and actually you can calculate what the distances roughly may be. And on the basis of the intensities, you can actually see the total structure of the molecule. Draw the structure of the molecule. There are two extensions which is given here at 6.1 and 6.2. Oh, the 12 is indicated here, you see. 12 is showing, what is this here? 12 is here. 12 is showing to these ones there, NOEs at 6.1 and 6.2, ppm 6.1, 6.2. Those are not part of this. These are outside this range. Until 3 ppm, this is the same as this. But you have something which is down here below in the 6.1, 6 ppm around. So these are the protons which are close to oxygens. Are they close to oxygen? 6 is, there is a 6 here, and there is a 5. At 6, there is also some other proton, it looks like. 12, there is no oxygen here. 12, there is no oxygen.
Yes, sir. 12 is this one.
This is not 12. What is this here?
This is 12 here at the center of the molecule.
Oh, here it is 12. Okay, this is different. This is the methyl. Okay. 12 is here.
Yes.
Okay. So the 12 is showing to a proton which is to 3 protons there. 6. 12 is showing to 6. This is NOE.
Yeah.
This is NOE.
Yes.
And 12 is showing to 8 prime.
Yes.
And is also showing to 5 prime. And these ones are at
so out of that 6.
so 12 is far away, no? So 12 is close to this oxygen. That's why this is shifted down.
Yes, sir. Then it is attached to 2 oxygen.
It's 2 oxygen. Therefore, it is quite down, around 6.15 ppm. And that is showing to this ones there. So combination of this, all these NOEs will confirm the analysis part. Okay. All right. So this can be continued. I mean, those of you who want to do more on this, go through every one of these peak and establish the connectivities. Okay.
See, it does not have any cozy relation because all surrounding all are carbons and cotton.
Yeah, 12, no?
Yeah.
12, yes, that's correct.
So there is no cozy.
There is no cozy, that's why this spectra does not contain that portion at all,
Yes.
that region at all.
Yes.
So all others are quaternary carbons and therefore.
Showing up in those.
Correct. This is the singlet here, and you are seeing NOEs on directly to this ones which are close by in space. Okay. Now let's go to heteronuclear spectra. So those were homonuclear spectra. This spectra I had shown in the when we are actually talking about the experimental sequences also. But I'm putting them back here because to help analyze the spectra, analyze how to do the analysis here. And this is the HSQC spectrum of this molecule. The carbons, this is the carbon spectrum here and the proton spectrum there. Again, all the assignments are given. All the assignments, these are 22. This is a very large number of protons there. All the way from here to 1.0 ppm to 6 ppm, there are 22 protons. Okay, there is also 23 there. The 23, that's carbon probably. The labeling is carbon.
Yeah.
Labeling is of carbons. Okay, and then you have the protons which are there. So 23 carbons, and the corresponding protons are indicated by the carbon numbers. So these are 15A, 15B. So the carbon 15 is here. Carbon 15, this is carbon 15, and this is connected to A and B. Those are these two there. These two there. Carbon 15. Now look at the next one, 14 carbon. 14 carbon is here. Notice here we are talking about one bond correlations only. In the HSQC, we are seeing correlations to directly attached to proton. So the carbon on one side and the proton on the other side. And you see 14 is one carbon, directly only one proton. So therefore that is giving you. And the other one you see here 11, where is 11? 11 is attached to two protons, A and B, and those ones are here. And 17 is here, 17 is this one. This also ought to have two, A and B, but only one is seen. Probably the two are equivalent.
Yeah, that peak intensity is also.
Intensity is more, the A and B are possibly equivalent here. So 17, A and B, they are only one peak is seen. So 13, similarly only one. Where is 13? 13, only one proton is there, therefore no problem. 13 is indicated here. And 18, where is 18? 18 again has two protons, so 18 doublet, these two protons there. And 20A and 20B, quite far apart. 20A, so these ones, A and B, once again they are very different. A and B are different. All these things actually they reflect upon the stereochemistry of the molecule. And how is the free motion? Is that free motion possible there? Then if the free rotation is, then they become equivalent. But if the free rotation is restricted, then of course they will become non-equivalent. And 16 is where is 16? 16 is only one proton, therefore only one peak there. And 8 and 16 are overlapping probably. Where is 8? Here. 8 is here. So 8 and 16 are equivalent, it looks. They are adjacent here. And 23 is again 23.
Two protons are.
Two protons, they are again equivalent.
Yeah.
Very close by, very close by. And 12 is only one proton, no problem. So 22 is only one proton, that is here. And 1 is, okay, these are the aromatic ones there. 1, 2, 3, 4. 1, 2, 3, 4, these are all aromatic ones. And they are at a different proton chemical shift wide away. So all others are not aromatic ones. These are all cyclic, yes, big cyclic molecules. Yeah. So this is the HSQC is quite clearly understandable there. And then this is the HSQC toxi. Now you made a relay here. So this is the, let's look at the top one there, 15A, 15B. So this is 15 here, 15A, 15B. These peaks are the same as 15A, 15B as in the HSQC, but you are seeing relays to 14 and 16. So where is 15? 15 is here. 15 you are relaying to 14 and 16. This is because these protons are coupled to this. This proton is coupled to this. Therefore, there is a relay from 15 to 14 and 16. So when you determine the structure, this must be consistent with your spectra. So all the peaks which are coming, it must be consistent so that you can analyze this. You can confirm the structure of the molecule. So let's look at this one there. This is number 12, right? So the 12 is showing to this one there, 16. 12 is showing to 16? No, can't be 16. Or 8 is it? Where is 12? 12 is here.
So 12 is connected to 13, 11.
This is 12, isn't it?
Yeah.
So this is 12. This is connected to this. What is this peak there? So 12 here in the HSQC, it is not showing to anything. But in the toxi, it is showing to 20A, 14 and 8. These are too far. How does that come? 12 to 14.
12 to 14.
12 to 14 is possible. That is possible. 12 to 14 is possible. Okay. Now once you have the 14 there, then the relay can happen from there onwards. Oh, 8 is here.
Yeah, 8
Yeah, 8 is also possible. 12 to 8 is also possible.
15 is missing.
And which one is this one? 20. Can it go to 20?
No, sir. Copy the.
20 के तो लेकिन कौन सा है? 11 is it? 11B, where is 11? 11 is possible.
11 is first.
So that is next one, that is 11.
So 11, 12, 13, 14.
11, 12, 13, 14. So you have that
Eight.
kind of correction. Yeah,
and eight.
yeah. So therefore, you see, this kind of analysis is going to be extremely useful for arriving at the structure. And this one is what? This is 22. 22 is showing to 23.
23 and,
इधर ही है.
and the other carbon is not labeled. I think we connected to that also.
22 is this. 22 is connected to 23. And this carbon is, because this is the quaternary one.
Yes.
There is nothing there.
Nothing important, right.
So 23, and then you have this one here. This one is 14. Is it 14 or 18?
14 से हो सकता है. 14 is
14 से हो सकता है?
Yes.
22. This one is here.
Yes.
So it is possible.
And 20. And 20 is here also.
20 is also, or 20 is also very weak one you can see. There is a small tiny dot there, which you can see. Yeah. So there is so much, that is the use of this HSQC toxi. How the relay happens, you can figure out the nearby ones. Okay. Now, the same molecule, the noisy spectrum. See, once again, the noisy spectrum has red peaks, which are NOEs. The red peaks are the NOEs. So the structure calculation now. So far, the toxi and the HSQC spectra you use for assigning the individual resonances. And now to calculate the structure, you need to have what all possible short distances are there. And that comes from the NOE. The NOEs, you can see very beautiful NOEs there from, see, let us take at this 15. The 15 is, these were the two toxi peaks, right? The toxi peaks. Toxi, this is 15A and 15B. 15A and 15B, these were in the HSQ, this is HSQC spectrum. They are HSQC peaks. Okay, now HSQC nosy it is. So therefore, from 15 proton, you are seeing NOEs to 16 to 20B and to 11 or 14, which is close by. 14 is close by. You are seeing to this is 14. 15 to, you are seeing to 20B. Where is 20? 20 is here. So from these protons to these protons, we can see NOE. That's not far. We can see 20B, one of them. You are seeing only one of them. Remember, notice that. I know you are seeing both. No, 20B, there are two protons. Okay, there is seeing to 20B only, not 20A. Where is 20A? 20A is here. You are not seeing to that. You are not seeing to this. You are seeing only from this to this. You are not seeing to A. So this will tell you about the stereochemistry there, right? Which one is going down, which one is going up, which is coming close by. And you are also seeing to 11. 15 to 11. Where is 11? 11 is far. No, this may not be 11 then. Is it 14? Yeah, 14. 14 you can see. This may be 14.
Yeah.
This is 14. And 16? 16 of course is possible. There only. It is close by. And that is, you can see the NOE from there. Okay. So, let's look at this one here. 12. 12 is showing to this one, and this one. There are three there. 12 is, where is 12? 12 is here. 12 is showing to 23.
11 will be 11, 13.
11, 20, 23 is showing.
23 will come. 23.
23 is here. 23, this will come.
23A will come.
23.
13, 14 and 11.
Yeah.
4 possibilities.
14 is here. 13 is here. And 11 it is not showing. Where is 11? 11 is here.
This side.
It's here. Oh, it's here. This may be the 11 one. Yeah. You are seeing to 14, 11 and 23. So therefore, this will confirm the structure.
So how we calculate the percentage means the distance?
Approximately on the basis of the intensity.
So number of circles.
Number of circles, yes. On the basis of the intensity, you roughly estimate that you don't want to say it is exactly 3.5 angstroms or 3.8 angstroms. You will say, okay, this is further than this. That much you can say. because the quantification of the NOE is not going to be so precise. That therefore, when you have a large number of NOEs, you can actually calculate the structure to be consistent with the approximate variations in the intensities. So when the intensities are similar, then of course it will mean that, okay, they have similar distances. So that will actually allow you to calculate the structure. Therefore, you see here in the structure also, it is indicated which one is going down, which one is coming up. So this stereochemistry is quite clearly indicated there, and that is consistent. That must have been derived from the NOESY spectrum. So the normal two-dimensional NOESY, you cannot get this. The normal 2D proton NOESY, you cannot get this sort of a detail. Here, because of the carbon resolution which you have got, you are able to identify the individual NOEs and quantify those ones. And when these are proton NOEs only, but using the carbon resolution to individually identify the NOEs and quantify them. That is, if you look at, for example, this distance is longer than this distance. That is with respect to what, let us say 15. 15 is here. Okay, 15 to 16 is close by here. 15 to 20 is further away. See, this one is further and this one is closer. This intensity is higher than this. So you can put qualitatively like this intensity patterns in the computer to build the models. Okay, so now that is so much for this organic molecules. Maybe Ghosh will cover more of those ones later.
Yeah, so this is in the next class.
I think we will take this to the next class. So this is amino acids and how to analyze amino acid spectra.
So when you have mixed red color, now you can use different color pen from here. So there you can. So थोड़ा कभी-कभी आपका डॉट गिरता है ना, confused हो जाता है whether it is coming across.
Oh yeah. I choose the color.
You can use a different color pen.
Yeah, I think that's better. When there is already that color is there.
Yes. So.
Okay, I will use
that
this.
When they will read it, na?
They will see as a
Is
signal.
this better? This one?
Yeah, you can use blue or green.
I will use this.
See this color which is not there in your
Yeah.
picture.
That's right. But almost all the colors are pink and yellow and.
No, in the previous diagram, na? See this.
Yeah, here.
Oh, when you are putting a dot, na? So.
Oh, yeah. That is right.
The cross peak or your pen.
It will show up there. It will remain like that.
Your original file, it will not be there.
No.
But when you recorded one, it will be.
I will remove this. Where? Okay, now I put these lines also. Whichever one I have put, it can go. Yeah.
So, and then in those cases.
I think I can use a different color pen. That is a good idea. Yes.
Then your master copy as a reading material, they will have the.
They will have the original one.
Yes.
Master copy it will be original.
Original one. Yeah.
Recorded one, these dots will be there.
Yes. Yeah. Okay. So yeah, we will change the color in the next one.
Yeah.
Now of course I will already change it. Yes.
Yes.
This is the
So
sign.
there are, I think, 2, 3, 4 colors are there.
Yes.
Okay, sir, you
So
can.
shall we stop here?
Yeah, so
Stop it here.
just both these are not stopping.
Okay, we are stopping here now.
The students in just.
And any questions?
Question, doubt, chat.
Any doubt? Just write any doubt.
So Friday I will finish this particular set and that will be the end, right?
That's okay, no? So it will be comprehensive. The rest of the things Dr. Ghosh can.
Yeah, then I'll start from next week. If you need, you can, if you feel that you still something to be told.
No, I think anyway, some of these things will be covered in the next module.
Next module.
Biomolecular NMR.
Yeah, that again it will be.
That it will again, some of that will come again.
So you need not to go in depth to the bigger molecules.
Yes,
Just,
here I will not go into the
yes.
bigger model.
Just for
Yes, the peptide amino acids and peptides, I'll show that much only. So next class we will take 1 hour only.
Okay, okay.
Sir, there is a.
1 hour, 1 hour.
Huh?
There is a very good question.
What is it? We can suppress water peak, can we suppress other peaks? Yeah, you can suppress other peaks also. The same strategy, you have to keep the carrier on that peak, whichever one you want to suppress. Okay, and there are also ways of designing currently using shaped pulses where you can actually suppress multiple peaks. But these strategies are also there in the modern spectrometers. You can do that. You have to design a peak shape, pulse shape, not peak shape, the pulse shape which will actually suppress more than one peaks. Watergate and things like that, what we discussed, that is actually to suppress the water peak. And then, however, if there is no water, suppose there is another big signal which is not water, but then you can suppress that also using the Watergate, but you have to keep your carrier on that peak, not on the other place. Whichever one you want to suppress, you put the carrier on that peak and use the Watergate. There is also things like excitation sculpting. There are many methods which are there. We have taken only some small numbers of that. There is a jump return sequence and 1-1 sequence, 1-3-1. There are so many different kinds of sequences which are used for suppressing the water signal. But whatever can be suppressed, whichever signal is large, you want to suppress it, you can use those pulse sequences. Accordingly, you have to adjust the carrier position. Did you get it?
Whether it affects.
Intensity of other signals. Not much. If there is anything which is under that signal, of course it will affect it, but not much. See, we are approximately will have to optimize the power and all of those things you have to optimize. See, some intensity
is very important. How much
yeah,
power and
how much power you use for that, and see over the whole range. Suppose you keep the water, you are suppressing the water, and look at the amide protons. Amide protons, there will be small variations in the intensities, but that is okay. That will not distort the intensities too much, but there will be some small effects will be there because the excitation profiles of the jump return sequences. Watergate will not do that, but the jump return and other sequences, it can cause a small distortion of the intensities in the other regions as well. The central portion of that region of interest remains the highest, and others there will be small changes in the intensities. That is, there you are not worried too much about the intensities, but you are worried about the observing the signals per se and suppressing the water. But the Watergate will not have that. Excitation sculpting, there is another sequence which is there, which will not even have that. Today we use mostly excitation sculpting as the suppressing technique.
So one thing, so see, suppose some protons are exchanging, like amide proton is
Yes.
water.
Yes.
Watergate, will the intensity
The
of
saturated signal, yes, it will affect that.
like that
will
will
affect
affect.
that.
So their intensity will be
It will
drastically
affect that,
reduced
yes,
because of the exchanging.
that's right. The exchange will cause reduction in the intensities. Yeah, this will be more in the case of direct saturation.
Yeah.
If you're using direct irradiation on the water, then the saturation transfer will be far more.
Okay.
But in the case of Watergate, it is not so much. Is with the gradient enhanced suppression what it is, it will not be so much.
But it will be slightly affected.
It will be slightly affected.
Because of the exchanging, I will cover the
Yeah.
dynamic part of the dynamics of dynamic
Yeah.
mass spectroscopy.
Yeah.
But the thing is that whatever depth you are teaching,
Yeah, yeah.
I will not be able to correlate those things into my thing because
That is fine, no? So therefore we will have
Yeah.
multiple
Yeah.
this one perspectives of that.
yeah.
So the students will get the overall.
But once they understand the principle, they will be able to correlate.
Yeah.
Okay. Okay. So उसको attendance ले लिया ना? Okay, then we will meet on Friday. So we will meet on Friday.
Yeah, Friday we will meet, and I will take one lecture on Friday.
So it will take 1.5 hours. Means we'll keep option like that.
Whatever time it takes.
Just tell us
Finish
if they have any doubt, na? Go through your portion.
Right.
You say, sir, this Friday will be your last talk.
Last talk.
So any doubt they are having, they can ask.
Yes. So you remember, all of you heard it. Friday will be my last talk. And any questions you might have, you can bring that up and we will clarify that further. On any topic. Not only on the today's or yesterday's,
Yes.
any topic, whatever we have covered so far, on anything you have a question, you can ask.
Okay then?
Okay, sure.
Close it now.